Achieving single-token decode pipeline parallelism on Apple Silicon requires splitting the workload. We need to offload the LLM feed-forward network layers, the dense mathematical operations that process individual token representations, to the Apple Neural Engine, while the GPU simultaneously handles the attention mechanism, which calculates the relevance of past tokens. The hardware incentive for this split is massive. For a 3 billion parameter model, the Neural Engine achieves a highly competitive dispatch latency of approximately 117 microseconds. The primary obstacle is software architecture. The Neural Engine hardware is locked behind an undocumented private Apple framework called ANE services. This effectively blocks standard execution using MLX, which is the standard array framework for machine learning on Apple Silicon. Standard hardware training approaches fail entirely on this chip architecture due to kernel-level traps. To bypass these protections and hit our performance targets, we have to construct a custom asymmetric synchronization pipeline from scratch. This diagram shows the structural difference we need to achieve. The left side outlines the baseline MLX decode loop, which is strictly sequential, CPU to GPU, back to CPU. The right side illustrates our target pipeline, establishing simultaneous, parallel execution tracks for both the GPU and the Neural Engine. In this target architecture, the division of labor is absolute. We map the attention calculations strictly to Metal, utilizing the GPU, while the feed-forward network operations are isolated and sent exclusively to the Neural Engine. This specific routing achieves perfect zero-copy hardware concurrency. Understanding the exact mechanics of this design requires mapping the undocumented kernel walls that force the pipeline into this configuration. The logical first step for executing models on the Neural Engine is mapping user-land memory directly to the hardware using the internal INE Program I/O Surfaces mapper. I/O Surface is macOS's standard framework for passing graphics and media memory efficiently between processes. This diagram illustrates what happens when you attempt that direct memory map. The user-land payload tries to write to the Neural Engine's IOMMU, or Input-Output Memory Management Unit, which controls the hardware's physical page tables. The system immediately forces a hard rejection, throwing a specific 0x1D kernel error. The Apple H16ANE interface kernel driver triggers this 0x1D error, because it scans the binary for Apple's private memory unwire access entitlement. Because third-party code lacks this private key, the driver rejects the write request entirely. To bypass the kernel block, we have to route this memory over XPC, Apple's inter-process communication protocol. We send the memory descriptors to ANED, a privileged system daemon that already possesses the required entitlements, allowing it to write to the IOMMU on our behalf. Executing code on the Neural Engine requires surrendering direct memory control. You must incur an indirection penalty by marshalling every instruction through Apple's privileged background process. Once memory is successfully marshaled, the standard approach to achieve pipelining is to natively link the Neural Engine and GPU tasks using Apple's internal _ANE chaining request API. This chart tracks the execution results of exhaustive testing on that chaining API. We swept through single model configurations, 2 model sequences, and applied selector 8 mutagenesis to test alternative execution paths. Every single path returns a hard code 15 error. The native chaining API is heavily daemon-gated and completely dead for any third-party implementation. It cannot be used. The required fallback is a manual zero-copy solution. We instantiate 2 separate INE in-memory model instances and configure them to share a single intermediate I/O surface buffer, passing the raw memory without duplicating it. Firmware protections make native task chaining impossible. We have to manually orchestrate the hardware handoffs by actively manipulating the shared memory surfaces ourselves. Manually sharing an I/O surface buffer requires exact bidirectional hardware signaling to avoid race conditions. The GPU must alert the Neural Engine when to start, and the Neural Engine must alert the GPU when the math is finished. The signaling from Metal to the Neural Engine functions correctly. We achieve this by binding a hardware wait event directly to the GPU's MTL shared event. This terminal view captures the failure in the opposite direction. Attempting to signal from the Neural Engine back to Metal crashes the entire system. At memory address 019F22DD54, the framework executes the BRAA instruction. That BRAA instruction dictates pointer authentication, a hardware security feature verifying memory addresses before executing them. It attempts to branch on an undocumented Objective-C completion block meant only for Apple's virtual machine environment. Because that block is missing in standard userland, the pointer resolves as null, triggering a SIG-seg, a segmentation fault that causes a full XNU kernel panic. The hardware feedback loop is broken in userland. We cannot rely on the neural engine to signal the GPU, meaning the pipeline's choreography requires a total redesign. This flowchart breaks down the final architecture, the asymmetric synchronization pipeline, which completely abandons the neural engine to Metal signal. Step 1. The CPU dispatches the attention shader directly to the GPU command queue. In Step 2, the CPU dispatches the feed-forward payload to the neural engine. However, we apply a hardware weight tied to the GPU's shared event. The neural engine receives the payload, but sits dormant. Step 3 is the crucial pivot. The CPU does not wait for the processors. It immediately frees itself and begins preparing the KV cache for the next token. The KV cache is the memory structure that stores past token states during generation. In Steps 4 and 5, the hardware resolves the sequence. The GPU finishes the attention math, which automatically triggers the neural engine to wake and compute the feed-forward layer. When the neural engine finishes, it bypasses the GPU entirely and wakes the CPU using a legacy, synchronous I/O fence interrupt. By enforcing an asymmetric signal flow, we avoid the pointer authentication trap entirely while preserving perfect zero-copy concurrency between the two hardware blocks. Relying on the legacy I/O fence interrupt introduces a specific bottleneck. Abandoning a pure hardware-to-hardware signal means we incur an XNU context switch latency penalty when the CPU is forced to wake up. This stacked bar chart maps out the multi-process sampling of that latency penalty. We record under 5 microseconds for the physical silicon handoff, roughly 15 to 20 microseconds for the I/O connect call struct method kernel trap, and another 15 to 20 microseconds for the XUNU context switch. This nets out to a median, or P50, latency of about 17 microseconds. In a production environment, this 17 microsecond penalty is mathematically irrelevant. It is entirely absorbed by the concurrent CPU work preparing the KV cache we established in Step 3. The CPU is already busy when the interrupt occurs, hiding the delay. As context lengths increase, the neural engine offload easily hits its break-even point. By systematically mapping out the kernel traps and hardware dead ends, we can successfully bypass Apple's private frameworks and execute high-performance MLX inference on completely walled-off silicon.